All right. Hi, my name is Anthony. I'm here with Kofi, and we'll be reviewing we'll be end of the project,
Yeah.
analog circuits. So regarding the circuit, since we have to answer a couple questions, I'll just be reviewing our notes. Regarding the poles, zeros, and phase margins, the OTA has one dominant pole at the output and one high frequency pole at the cascode folding nodes. There's a small left half plane zero. There's approximately 72% phase margin. Um, we achieve that by pushing the non-dominant pole above the unity gain. We use low parasitics and we change the sizing. Some main challenges were the DC convergence. We had some issues with wiring things properly from schematic to layout. What else?
We're trying to get each individual device in saturation. So if you look at the screen, one thing that we try to do, or at least I try to do, is remove the biasing circuits right from there, and then use these references and the pins. And these pins will have a specific voltage, and I could do a DC sweep through them. So I did about I don't know, about 20 DC sweeps with each reference point. So this has its own variable. Here, let's click in there so you can see. So this was VBB, VBP, so on and so forth. Let me come over here. So something as this, right? So this will be an example. And then we have our parametric sweeping will be something of an example that we did here. So we swept it from 0.1 to 5, and then the graph, based on the graph, will pick that value and then insert it back in the design variables. So we kind of iterated on this until we got close to everything being, or some of it being close to saturation as possible. Right. Cancel.
So, regarding the question of increasing the output capacitance, we found increasing it to 20 pF by moving the dominant pole lower, we were able to increase the load capacitance and reduce the bandwidth along with the unity gain frequency. And the phase margins we found almost stayed the same uh, because of the internal non-dominant pole. It didn't change. Uh, in order to improve performance for gain, we decided to increase cascode channel length.
Yes.
That increased the output resistance. For bandwidth, we increased the pair current, and that increased GM.
Yes.
We reduced the cascode GM, and that pushed the non-dominant pole higher, and that was for the phase margin. That's how we approached that. Some advantages we found was the very high DC gain and had a good power efficiency. Um, and this was most likely due to the cascoding of the single stage design. Some disadvantages of this was that the limited output swing and there were some stability issues.
Yes. Just to add on to what Anthony was saying, on the top here is where most of the that contributed most of the R out. So we know the gain equation is AV equals negative GM R out. So the PMOS part is what contributes most of the resistance. And the initial part right here, the input pair or the input differential pair contributed to the specific GM. So once you get your GM, you kind of adjust things here to get your GM. And then when you go up here, you adjust things to kind of get your R out in a sense. Also changing the widths of the transistors. So for example, changing the width of the input pair, you would effectively kind of increase the gain of them. Uh, Changing it for the PMOS as well gave the same type of result.
All right. And that concludes it.